Ever get that feeling? Like you're just drowning in data, and you're like, man, I wish there was a cheat code, some way to just like unlock the real meaning behind all these
Oh,
numbers.
yeah, totally. We all crave that shortcut to understanding, right? Especially when things seem random and overwhelming.
Exactly. And that's kind of what we're diving into today. It's like a cheat code for understanding a huge amount of data out there. We're talking about the normal distribution, sometimes called the bell curve, sometimes the Gaussian distribution, all the same thing.
That's right. And you, our listener, sent in some amazing material on this. Stuff that explains what the normal distribution is, how it behaves, and most importantly, how we can use it to actually make sense of the world around us.
Awesome. So our mission today, extract those key insights, the practical takeaways, without getting lost in the weeds of super technical statistical theory. We're keeping it clear and applicable.
Absolutely, making it relevant for everyone.
Okay, so first things first, this normal distribution. We keep hearing the name. What is it, really? What makes it so special?
All right, picture this. A nice, smooth hill, perfectly symmetrical, that classic bell curve shape. Now, imagine you're collecting tons of data points. Could be anything, right? Test scores, heights, whatever. If that data follows a normal distribution, what you'd see is most of those data points clustered around a middle value. That's the peak of our hill.
Gotcha. So it's all about that central point where most of the data hangs out.
Exactly. And in a perfectly normal distribution, that central point is actually three things all at once. The mean, your typical average, the median, the middle value when you line everything up, and the mode, the value that pops up most often. All the same spot, right in the center of that curve.
Wow. Okay, so it's centered. Makes sense. But what makes one bell curve look different from another? Some are narrow, some are wide. What's up with that?
Ah, great question. That's where the mean and the standard deviation come in. So the mean, like we said, tells you where the center of that bell curve is on your graph. But the standard deviation, think of that as the typical distance a data point is from that average.
Okay, I'm with you.
Now, if you have a small standard deviation, it means most of your data is huddled close to the mean. So you get a tall, skinny bell curve, but a large standard deviation means the data is more spread out. You get a wider, flatter curve. Same center point, just different degrees of spread.
Okay, I'm visualizing that. Narrow peak, wide peak. Cool. Now, the listener's material mentions something called the 68-95-99.7 rule. It sounds like a fundamental principle here.
Oh, it totally is. It's actually a big reason why the normal distribution is so powerful. It helps us make these probabilistic statements about the data without having to analyze every single point.
Sounds like a time saver.
Definitely.
Yeah.
And the 68-95-99.7 rule, it's basically a shortcut for understanding how spread out the data is around that mean. It tells us that around 68% of all data points will fall within one standard deviation of the mean. That's on both sides, above and below.
Like one standard deviation, 68%.
Got it. Then, if you go out to two standard deviations from the mean, you're capturing about 95% of the data. And if you stretch all the way to three standard deviations, boom, you've got a whopping 99.7% of all your data points covered.
Wow. Almost everything is within those three standard deviations. So just knowing the average and how spread out the data usually is, you can get a really good idea of where most of the data lies.
Precisely. And the material gives a great example to illustrate this. They talk about the heights of adult males in North America, where the average, the mean height is 70 inches, and the standard deviation is 4 inches.
Okay, heights, inches. Classic example.
Now imagine we want to find a height that's 2 standard deviations above the average. What we do is we simply add 2 times the standard deviation to the mean. So 70 plus 2 times 4. That gives us 78 inches.
So a guy who's 78 inches tall is quite a bit taller than average, thinking about how the data is typically distributed.
Right. Now let's use the same height example to see that 68, 95, 99.7 rule in action. Remember, about 68% of the data falls within one standard deviation of the mean.
Right.
So if we go one standard deviation below the average height, we get 70 minus 4, which is 66 inches. And one standard deviation above the average is 70 plus 4, which is 74 inches.
So basically, 68% of men in North America are somewhere between 66 and 74 inches tall.
That's the idea. Simple, right?
I like it. Okay, what's next?
Next up, we've got z-scores. This is where things get even more precise.
Z-scores, I've heard of them, but honestly, a little fuzzy on the details. Sounds like it helps you pinpoint exactly where a specific data point fits in.
You got it. See, we understand the overall spread now, but what if you, our listener, have a specific data point and you're curious, How unusual is this? Where does this sit in the grand scheme of things? That's where z-scores come in.
Okay, so it's like giving every data point its own unique address based on how far it is from the average.
Exactly. And this address is measured in terms of standard deviations. A z-score tells you precisely how many standard deviations that data point is away from the mean. And importantly, it tells you if it's above the mean, which gives you a positive z-score, or below the mean, which gives you a negative z-score.
So positive z-score above average, negative z-score below average. Makes sense.
Right. And if a data point happens to land exactly on the mean, its z-score is always 0.
Dead center. Okay, I'm getting the picture. But how do we actually calculate this address, the z-score?
Fortunately, the formula is pretty straightforward. You take your individual data value, subtract the mean, that average of the whole distribution, and then divide that by the standard deviation. So it looks like this. Z equals, in parentheses, data item minus mean, close parentheses, divided by standard deviation.
Okay, I'm going to need a real-life example here.
No problem. The material mentions newborn baby weights. The average weight is 7 pounds, and the standard deviation is 0.8 pounds. Let's say we have a baby who weighs 9 pounds. What would their z-score be?
All right, let's plug it in. So 9 pounds, our data item, minus 7 pounds, the mean, equals 2 pounds. Then we divide that by the standard deviation, which is 0.8 pounds. So 2 divided by 0.8, let me see, that's 2.5.
You got it. So a 9-pound baby has a z-score of 2.5. That tells us this baby's weight is 2.5 standard deviations above the average weight for newborns.
Wow, that's a pretty hefty baby, statistically speaking.
Right. Now, can we work this backwards? Let's say we know the z-score. Can we figure out the original data value?
Ooh, that's a good question. Can we?
Absolutely. Let's take IQ scores, for example. We know those tend to be normally distributed with an average IQ of 100 and a standard deviation of 16. Let's say someone has a z-score of negative 1.5. What would their actual IQ be?
Negative z-score. So this person is below average, but by how much?
Okay.
How do we reverse the formula?
It's just a little rearrangement. You multiply the z-score by the standard deviation and then add the mean. So in this case, negative 1.5 times 16 plus 100, that's negative 24 plus 100, which gives us an IQ of 76.
76, okay. And that negative z-score confirmed that this IQ is indeed below the average of 100. Pretty neat.
Exactly. It all fits together. And what's really cool about z-scores is that they let us compare data points from completely different data sets, even if they have totally different means and standard deviations.
Right, because we're essentially putting them on this common standard deviation scale.
Exactly. Now, let's shift gears a bit and talk about ranking data within the normal distribution. Enter percentiles and quartiles. I bet you've heard these terms before.
Oh yeah, percentiles and quartiles. Definitely heard them, especially when talking about standardized test scores and how you stack up against others. But what do they really mean in the context of the normal distribution?
Good question. A percentile basically tells you the percentage of data that falls below a particular value within a distribution. So let's say a data point lands at the 80th percentile. That means 80% of all other data points in that set are smaller than that one. Simple as that.
Okay, 80th percentile, 80% below. I got it. Now quartiles, they're like special types of percentiles, right?
Right. They divide the data into 4 equal parts. So the 25th percentile marks the first quartile. 25% of the data is below that. The 50th percentile is the second quartile. And here's the interesting part. In any distribution, this is also the median.
Right, the middle value.
Exactly. And finally, the 75th percentile is the third quartile, with 75% of the data falling below it.
All right, quartiles, dividing the data into fourths. Now, how do these percentiles and quartiles connect back to those z-scores we were talking about?
Ah, that's where the magic happens. In a normal distribution, once you've calculated a z-score for a specific data point, you can actually use what's called a z-score table. It's also sometimes called a standard normal distribution table.
Okay, a table. I'm assuming this table helps us with something.
Big time. This table tells you exactly what percentage of the data falls below that z-score, which is essentially its percentile. The listener even provided some example data from this table. A z-score of 1.4 corresponds to the 91.92nd percentile. A z-score of 1.5 corresponds to the 93.32nd percentile, and a z-score of 1.6 corresponds to the 94.52nd percentile.
Huh, so those z-scores are like keys to unlocking the percentile information in the table. Pretty cool.
It's a powerful tool. And something else important to remember, in a perfectly normal distribution, the mean itself, which remember has a z-score of 0, corresponds to the 50th percentile, which makes sense, right? Half the data below the average.
Makes total sense. Okay, let's switch gears a bit. The listener's material also mentioned margins of error in polls and surveys. How does the normal distribution fit into that?
This is a fantastic real-world application. You see, when statisticians conduct polls, they're only surveying a sample, a small part of the whole population, right?
Right. It's impossible to ask everyone.
Exactly. And they know that the results they get from their sample might not perfectly match the views of the entire population. So the normal distribution comes in to help estimate how reliable those sample results actually are. The margin of error is basically a way to quantify that uncertainty.
Okay, so margin of error, uncertainty. Makes sense.
Now, here's the cool part. If you have a randomly selected sample of size n, there's a 95% probability that the true statistic for the whole population falls within a specific range around the sample result. That range is calculated as 1 divided by the square root of n, and that value, that 1 divided by the square root of n, is often what's reported as the margin of error.
Hold on, square root. Why the square root?
That's a great question. The square root in the formula comes from the central limit theorem, a really important concept in statistics. It basically describes how the variability of sample means decreases as you get a larger sample size.
So the bigger the sample size, the more confident we are that our sample reflects the whole population, and the smaller our margin of error.
Exactly. And the material provides a perfect example. They talk about a survey of 1,000 U.S. adults where 46% said they dreaded public speaking. Now, the margin of error for a sample size of 1,000 is about 1 divided by the square root of 1,000, which is roughly 0.032, or 3.2 percentage points.
So even though the poll found 46%, the actual percentage in the whole U.S. population could be a bit higher or lower.
Precisely. With this margin of error, we can be about 95% confident that the true percentage of all U.S. adults who dread public speaking lies somewhere between 46% minus 3.2%, which is 42.8%, and 46% plus 3.2%, which is 49.2%.
Got it. So that 3.2% margin of error gives us a range where the real answer probably sits. Makes sense. Now, for the big question. Does all data follow this nice symmetrical bell curve?
That's where things get tricky. Not all data in the real world fits that perfect normal distribution. Sometimes we encounter what's called a skewed distribution.
Skewed distribution. What's that?
Imagine our bell curve, but instead of being perfectly symmetrical, it's kind of lopsided. The data piles up more on one end with a long tail stretching out towards the other end. The material uses weekly earnings in the U.S. as a classic example of this.
I get earnings, lots of people at the lower end, a few people making a ton of money. I can see how that wouldn't be perfectly symmetrical.
Exactly. That type of data often shows what's called a right skew.
Right, skew, meaning?
It means that the tail of the distribution extends towards the right, where the higher values are. On a graph, you see that big hump of people earning lower amounts, and then this long tail stretching out to the right, representing those few individuals with really high incomes.
Got it. So in a right-skewed distribution, the mean, that average, gets pulled higher by those extreme values.
Exactly. In fact, in a right-skewed distribution, the mean is usually higher than the median, which is higher than the mode. This is different from a normal distribution where all three are the same.
Okay, so knowing whether your data is normal or skewed is super important.
Absolutely, because if you try to apply the rules and interpretations we've been talking about for normal distributions to data that's skewed, you can end up with some pretty misleading conclusions.
So different data, different approaches. Makes sense. Now let's put some of this knowledge to work. The material you looked at had some problem-solving examples using normal distributions. Let's try those.
Great idea. Let's start with cholesterol levels. For males aged 18 to 24, cholesterol levels tend to be normally distributed with a mean of 178.1 milligrams per deciliter, MGDL for short, and a standard deviation of 40.7 milli-GDL. The question is, what percentage of males in this age range have cholesterol levels less than 239.15 milli-GDL?
Okay, so first step, if I remember correctly, is to calculate the Z-score for that cholesterol level, 239.15.
Exactly.
All right, so it's 239.15 minus the mean, 178.1, and then divide all that by 40.7, the standard deviation. Let me see, that's 61.05 divided by 40.7, which is, drum roll please, about 1.5.
You nailed it. A cholesterol level of 239.15 has a Z-score of 1.5.
Okay, Z-score acquired, now what?
Now we need to consult that handy Z-score table to figure out what percentage of males fall below that Z-score. Luckily, the material gave us some sample data from such a table.
Right. They said a Z-score of 1.4 corresponds to the 91.92nd percentile, 1.5 corresponds to the 93.32nd percentile, and 1.6 corresponds to the 94.52nd percentile.
perfect. And since our z-score is 1.5, we can see that roughly 93.32% of males in that 18 to 24 age range have cholesterol levels less than 239.15 milli-GDL.
That wasn't so bad. Let's try another example, maybe one with a bit of a range this time.
Sounds good. How about this? Let's look at the typical working hours of self-employed folks in the U.S. The average is 44.6 hours per week, with the standard deviation of 14.4 hours. The question is, what percentage of self-employed Americans work between 37.4 and 80.6 hours per week?
Okay, between two values. So first, we need z-scores for both those values, right?
Just got it.
Let's start with 37.4 hours. So 37.4 minus 44.6 divided by 14.4. That's negative 7.2 divided by 14.4. Gives us a z-score of negative 0.5. Now for 80.6 hours, that's 80.6 minus 44.6 divided by 14.5. Now, any of those percentiles?
Back to the table. The material said a z-score of negative 0.5 has a percentile of 30.85, and a z-score of 2.5 has a percentile of 99.38. Exactly. Now, remember, those percentiles tell us the percentage of people who work fewer hours than those values.
So 30.85% work less than 37.4 hours, and 99.38% work less than 80.6 hours. To find the percentage who work between those hours, we just subtract, right?
You got it. 99.38% minus 30.85% equals 68.53%.
So approximately 68.53% of self-employed Americans work somewhere between 37.4 and 80.6 hours a week. That's a pretty wide range, but it makes sense considering that standard deviation.
And that's exactly the power of these methods. They allow us to understand and analyze data that falls within a normal distribution, whether we're looking at single values or ranges.
All right, so we've covered a lot of ground today thanks to the material you, our listener, provided. We've really explored this concept of the normal distribution.
And I think it's safe to say we've accomplished our mission. We've extracted those key insights and practical takeaways without getting too bogged down in the technical stuff.
Totally. Big thanks to our listener for the awesome material. So let's recap. We started by understanding that the normal distribution is all about that symmetrical bell-shaped curve centered around the average, the mean.
We then delved into the 68, 95, 99.7 rule, which gives us a quick way to grasp how data is spread out around that mean. 1, 2, and 3 standard deviations.
We tackled z-scores, which help us standardize data points and figure out exactly how many standard deviations they are from the average, whether above or below.
And we learned how those z-scores connect to percentiles, allowing us to rank data points within a normal distribution using that handy z-score table.
We even saw how the normal distribution comes into play in the real world, helping us understand margins of error in those polls and surveys we see all the time.
We also touched on what happens when data doesn't follow a normal distribution and instead exhibits skewness, which can significantly impact our interpretations.
So much good stuff. I think this deep dive has really equipped our listeners with some essential statistical tools. Tools they can use to understand data in their own lives, work, and even when they're consuming news and information.
Absolutely. And as we wrap up, here's a final thought for everyone to consider. Now that you have a better understanding of this powerful concept, the normal distribution, think about how this knowledge might change the way you interpret information presented to you, whether in the news or your specific field of interest.
Yeah, think about it. When you see those numbers, those statistics, those reports, ask yourself, can I use this knowledge to gain a deeper, more critical understanding of what those numbers really mean? It's definitely something to ponder. Thanks for joining us on this deep dive.